Hello all. So far in the subject we have started with what are NLP applications, we have seen word embeddings, and then we have seen what is sequential labeling, language modeling, and then we have started with sequence to sequence model, and in unit 4 we have discussed about attentions and transformers. So we have covered a lot of ground so far, including many deep neural networks for NLP applications. We have used CNNs, we have used RNNs, the transformer models, and we've also uh, uh, seen many case studies on modern NLP frameworks like Hugging Face transformers and so on. However, we have paid very little attention to the details of training and inference. So, for example, like if you build a model, how do you train them? How do you train those NLP models, and how do we make predictions efficiently? How do we avoid having your model overfit? How do we optimize the parameters and so on? Because these factors could make a huge impact on the final performance and the generalizability of your model. So in this unit or in this chapter 5, we will cover some important topics that need to be considered to build robust and accurate NLP applications that performs well in the real world. Okay, so these are the contents that we're going to cover in unit 5. So we'll see what are the best practices in developing NLP applications. First is we're going to see about batching instances in today's session, followed by tokenization for neural models, hyperparameter tuning, how do we deploy and serve NLP applications. For example, how do we architect NLP application, how do we deploy the NLP model, and then we'll see one case study serving and deploying NLP applications, interpreting and visualizing model predictions, and then we'll see another important concept in the context of NLP, which is multi-model networks. Okay, along with this multi-model deep learning, we will also see image captioning, which is another important application of NLP. Okay, so we'll see image captioning on MS Coco datasets. We'll see how do we process the image with CNN, ResNet image, feature extraction with ResNet, and we will try to build a transformer model, training the transformer model with visual encoder and generating caption, improving the performance and state-of-the-art models. So first, let's begin with best practices in developing NLP application. That is the first topic for today is batching instances. So before I talk about batching instances, we've already seen how to build NLP application. There are basically 3 steps in building NLP application: the research stage, the development stage, and the operations. When I talk about research, we try to research on the problem statement and try to collect the data. Once the data set is collected, we go for analyzing the data and experimenting on that particular data set. After that, we train the model with the data, we implement that model, deploy, and then monitor, right? So we've already seen this 3-step procedure of building NLP applications right in unit 1. So when we talk about typical structure of model NLP application, we first take training data, like we read the data set, we develop the transformer model or any other NLP model, we train the data by using optimizers, and once the model is ready, we take a new instance and then apply that particular new instance and try to model the prediction. So basically we have 2 steps: training the data and then serving that particular model. Okay, so when we talk about training the data, we take the instance, okay, instance or labels, we give that to the model and we try to make the predictions. After we make the predictions, we'll try to calculate the loss function, and if the loss function is more, we apply optimizers, the forward pass, we apply back propagation, and then we update the model depending upon what the model is, depending upon how the model is updated, we again process and then give new instances and carry on with the development, right? So this is all known to us, right? So we have seen so many NLP models, right? Deep neural network models, RNN, CNN, transformers, and modern NLP frameworks like Hugging Face. So the most important things that we will focus in this unit are how do we train and make predictions efficiently? How do we avoid overfitting in our models? How do we optimize the hyperparameters? Okay, as I told you, because these 3 parameters make huge impact on the final or the overall performance of the NLP model that we develop. Okay, so we have seen so many NLP models, right? Starting with logistic regression, that is for sentiment analysis. We have seen RNN, sequential labeling task, and then language modeling, sequential labeling. We have seen sequence to sequence model, for example, machine translator, chatbot, and we have seen how to do text classification using CNN, sequence to sequence with attention, transformer model, BERT. We have seen NLI model, also natural language inference. Okay, now these are the three major things that we four major things that we consider when we want accurate NLP applications. First one, batching instances, that I am going to discuss in detail today. After that, we will also see how do we avoid overfitting of the model, how do we deal with imbalanced data set, and how do we do hyperparameter tuning. Okay, so let's start our session with batching. Okay, so we've already mentioned batching, a machine learning technique where the instances are grouped together to form batches and sent to the processor, whether it is CPU, GPU. More often we use GPU. Okay, so batching is almost necessary when training the large neural networks, that is the LLMs. It is critical for efficient and stable training, basically, right? So today in this session we will dive into some more techniques and considerations related to batching. Okay, now there are three important batching instance methods. The first one is called as padding, the second one is called as sorting, and the third one is called as masking. Okay, now let's talk about padding. Basically, when I talk about instances, or when I talk about batching the instances, the first thing that comes into my mind is padding. Okay, because training large neural network requires number of linear algebra operations, such as when we talk about linear algebra, we come across matrix addition, subtraction, multiplication, which basically, involve executing basic mathematical operations on many numbers at once. Okay, now this is why it requires, specialized hardware such as GPUs, TPUs, or other advanced processor designed to execute such operations in a highly parallelized manner. Okay, so what we do initially is we take data as input and send that to GPU as tensors, right? All of us know this, right? Tensors are nothing but high dimensional arrays of numbers. Okay, now along with some instructions, along the tensors, along with some other instructions as to, what types of mathematical operations it needs to execute and all. So the result is sent back as another tensor. The data is sent to the GPU as tensors. Once the operations are done, the result is sent back as another tensor. Okay, so we have already seen how do we like GPUs to factories overseas that are highly specialized and optimized for manufacturing the same type of products in large quantities, right? So because this is considerable overhead in communicating and shipping product, it is more efficient if you make a small number of orders for manufacturing a large quantity of products by shipping all the materials in batches rather than shipping materials on demand, right? So when we talk about this particular example, materials and products are usually shipped back and forth in standardized containers. If you have ever loaded a moving pod or trailer yourself, okay, you may know that, you know uh, there are many considerations that are important for safe and reliable shipping, right? So we sometimes need to put furniture and boxes in tightly closed boxes so that they don't shift around in transition. You need to wrap them with blankets. We use, bubble wrap covers and fix them with ropes to prevent them from being damaged. You need to put heavy stuff at the bottom so that lighter stuff won't get crushed and so on. So these are the basic measures that we consider when we're shipping our materials or products. So when I talk about batches, batches in machine learning are similar to containers for shipping stuff, okay, in the real world. So these batches are nothing but the containers for shipping stuff in the real world. Just like, shipping containers are all the same size and rectangular, batches in machine learning are just rectangular tensors. So please understand, batches are nothing but the rectangular tensors. Okay, now they're packed with the numbers of the same type. rectangular tensors packed with the numbers of the same times. If you want to shift multiple instances of different shapes in a single batch to the GPU, you need to pack them so that the packed numbers form a rectangular tensor. Okay. Now, when we talk about NLP, when we talk about context of NLP, we often deal with sequences of text in different lengths, right? Not all the sequences should be in the same size. So we receive sequences of different lengths, right? Because batches have to be rectangular, we need to do padding. Hope you got my point, right? So we do padding because batches have to be rectangular. So for that reason, we append special tokens called pad, PAD, to each sequence. We apply this pad to each sequence so that each row of the tensor will have same length. Okay, which means that you need to pad short sequences until they are as long as the longest sequence in the same batch. Okay, as you can see here in the figure, in reality, each token in natural language text is represented as a vector of length d. Let's consider a vector of length d generated by the word embeddings method. This means that, each batched tensor is a three-dimensional tensor which has a depth. D stands for depth here. Okay. Now, in many NLP models, sequences are usually represented as batches of NLD, N into L into D. Okay, as you can see in this particular figure, three-dimensional are represented as N, L and D. Okay, where N, L, D are the number of instances per batch. These are the instances per batch. The maximum length of the batch. This L is the maximum length of the batch, and D stands for the dimension of the word embeddings. Let me repeat. N number of instances per batch, maximum length of the sequences, and D stands for the dimensions of the word embedding respectively. Okay, so this is starting to look more like real containers. Batch 1, batch 2, batch 3. So this is how we perform padding and batching. Okay, now next, after padding, I would like to discuss about sorting. Okay, because each batch has to be rectangular. If one batch happens to include both short and long sequences, we need to add a lot of padding to short sequences so that they are as long as the longest sequence in the same batch. Now, this often leads to, because if suppose there is a sentence with one word and there is another sentence with 100 words, okay, we need to do so much of padding for short sequences. So basically this often leads to some wasted space in the batch. As you can see the first figure in this particular illustration. Okay, the shortest sequence is 6 tokens only. Okay, need now this to be padded with 8 more tokens to be equally long for this particular sequence. The largest here is 14 and the shortest one is only 6. Okay, so 8 more has to be added. So wasted space in the tensor means wasted memory and wasted computation process as well. So how do we avoid this? Okay, so can we avoid this, and if so, how do we avoid that? Now when I talk about this, we talk about reducing the amount of padding by putting instances of similar size in the same batch. So we put the similar sizes in the same batch. If shorter sequences or shorter instances are batched only with equally other shorter ones. Now they don't need to get padded with many padding tokens, right? So similarly, if longer sequences are batched only with other longer ones, that is shorter with shorter, longer with longer into one batch, as you can see here in the figure. Shorter with shorter, longer with longer one in one batch, separate batches. They don't need a lot of padding either because they're already long. Okay, so one idea is to sort. This is called as sorting. Sorting instances by their length and batch accordingly. As you can see here in the figure, this compares two situations. One in which the instances are batched in their original order, okay, and the other where the instances are first sorted before batching. These are sorted, and then the numbers below each batch indicate how many tokens are required to represent the batch. How many tokens are required to represent the batch, including the padding tokens. Now notice that the total number of tokens is reduced from 144 to 120. As you can see, the total number of tokens here is 144 and here it is 120 by sorting, because the number of tokens in the original sentences does not change, right? So this is purely because sorting reduced the number of padding tokens. So smaller batches require less memory to store and less computation to process, and sorting instances before batching improves the efficiency of training. So all these techniques sound somewhat complicated, but the good news is, you rarely need to write code for sorting, padding and batching instances yourself, as long as you use high level frameworks like Allen NLP or Hugging Face transformers. We have by default functions which you can use for performing all these operations. After padding and sorting, the next instance is masking. One final detail that you need to pay attention to is masking. Okay, so basically masking is an operation where you ignore some part of the network that corresponds to padding. Okay, this becomes relevant especially when you're dealing with sequential labeling or language modeling. Okay, so to recap or to make you understand, sequential labeling is a task where the system assigns a labels per token, right? NAR and POS. We have built POS, tagger and NAR models, right? So as you can see here in this particular figure, sequential labeling models are trained by minimizing the tokens, minimizing the per token loss aggregated across all the tokens in the given sentence, right? So we do this because we would like to minimize the number of errors the network makes per token. Okay, so this is fine. This will be fine as long as we are dealing with real tokens. Okay, as you can see here in the examples, time flies like in the figure. Okay, although it becomes an issue when the input batch includes padded tokens, because they exist just to pad the batch. They should be ignored when computing the total loss. So we usually do this by creating an extra vector for making a loss. Okay, uh, the vector for masking has the same length as the input, whose elements are ones for real tokens and zeros for padding. When computing the total loss, when we are computing the total loss, you can simply take the element wise product between per token loss and the mass and then sum of the result. Okay, so as long as you're building the standard sequential labeling models with NLP or Hugging Face transformers, you rarely have to implement the code by yourself. Masking is done by the POS tagger with the default function used. Okay, so this is all about batching instances by three techniques, which are padding, sorting and masking. Thank you.